Welcome back to Chemistry with Organic Chemistry course. I am Mr. Zenon Linaines, your instructor. So today, I'm going to discuss the measurement we are using in general chemistry, such as accuracy and precision, scientific notation, significant figures, and the standard unit of measurement or the SI unit. After this video, the students are expected to compare accuracy and precision, illustrate scientific notation, use four mathematical operation in identifying significant figures, and analyze a given problem using SI unit. So let's begin with precision and accuracy. Precision and accuracy are two ways that scientists think about error. Accuracy refers to how close a measurement is to the true or accepted value, while the precision refers to how close measurements of the same item are to each other. So these are the steps to determine if the measurements are precise, accurate, or not. So number one, add the trials. Number two, get the average by adding the trials and divide to the number of measurements. Three, identify the measurement if accurate or not by comparing the total average to the accepted value. 4. Identify the measurement if precise or not by subtracting the first measurement or highest to the second measurement and the second measurement to the third measurement. Then lastly, subtracting each measurement will determine if the measurements are close to one another or should be less than or equal to 1 to consider as precise. A classical way of demonstrating the difference between precision and accuracy is with a dartboard. Think of the bullseye or the center of a dartboard as the true value. The closer darts land to the bullseye, the more accurate they are. So look at the first dart, the letter A. If the darts are neither close to the bullseye nor close to each other, there is neither accuracy nor precision. So let's look at the letter B. If all the darts land very close together but far from the bullseye, there's a precision, not accuracy. Then for letter C, if the darts are all about an equal distance from and spaced equally around the bullseye, there's a mathematical accuracy because the average of the dart is in the bullseye. This represents data that is accurate, not precise. However, if you were actually playing darts, this would not count as a bullseye. Then for the letter D, if the darts land close to the bullseye and close together, there is both accuracy and precision. Now, let's test your knowledge using this problem about accuracy and precision. So there are 5 students need to measure on how much of the unknown substance they will put on their experiment. Each of them made 3 trials at different scales. Look which among their measurements are precise, accurate, or not in the standard measurement of the unknown substance, which is 70.8 grams, and also determine which among them is the most accurate. I will give you 1 minute to think of this. Now, let's check your answer. Student number 1, there is high accuracy, low precision. Student number 2, high accuracy, high precision. Third student, low accuracy, low precision. Fourth student, low accuracy, low precision. And the fifth student, low accuracy, high precision. Okay, so that's all for this lesson. I hope you just learned something for this lesson, accuracy and precision. So now let's move on to our next lesson, the significant figures. Okay, so significant figures are the number of measured quantities are counted but are not exact. Scientists use significant figures to determine how precise a measurement is. Also, significant digits in a measurement include all of the unknown digit plus one estimated digit. So this is the easiest way to understand how significant figures used in chemistry. So if you are measuring the volume of liquid using a weighted cylinder, you are reading at the bottom of the meniscus, the lowest point of the curved surface of the liquid. So let's say that the bottom of the meniscus lies between 55 milligrams to 56 milligrams, meaning the liquid volume is certainly greater than 55 milligram. If the instrument placed using the standard electronic balance, the result may 55.50 milligrams. The number 55 is the certain and the others are estimated digits. But if you weigh to a more sensitive balance, maybe the mass of the volume may vary. Even every measurement has some uncertainty which depends on the device used. All the digits in the measurement, including the uncertain last digit, are called significant figures, and zero may be included. So here are the rules for significant figures, or the rules in identifying significant figures. Number one, all non-zero numbers are significant. So for example, the number 55.5 has three significant figures because all of the digits present are non-zero. Second rule, zeros between two non-zero digits are significant. For example, 2021. 2021 has four significant figures because zero number is between 2 and 2. Third, leading zeros are not significant. For example, the number 0.56 has only two significant figures. Then, 0.000089 has two significant figures also because zero digits are leading in these values. Then, rule number 4, trailing zeros to the right of the decimal are significant. For example, 82.00 has four significant figures. The next, trailing zeros in a whole number with the decimals shown are significant. For example, 650. This value has three significant figures because the decimal shown in the value. Then, trailing zero in a whole number with no decimals shown are not significant. For example, 150 has only two significant figures because zero is not significant, or there is no present of decimal point. Then, for the last rule, for the number in scientific notation, for example, n times 10 raised to negative n. All digits comprising n are significant, but the first six rules, 10 and n, are not significant. So, 2.5 times 10 raised to 4 has significant figures. In this example, 2.5 times 10 is only a scientific notation of 2,500. So we will convert this value into a whole number to get the significant figures. So the significant figures in this value 2,500 with decimal point on the end is 1, 2, 3, 4. There are four significant figures in this value. So here are the other examples. For example number 1, 45.8736, there are six significant figures because all digits count. Then in example number 2, there are 3. Example number 3, there are 5. Then in example number 4, there are 5 because of the presence of the decimal point at the end of the numbers. Then in example number 5, there is only two significant figures because there is no presence of decimal point at the end. Then in example number 6, there is 4 because this is only a scientific notation of 3,982,000. Then in example number 6, there are 6 significant figures. Now, we will test your knowledge by answering this. I will give you a minute to get the significant figures of the following values. Then after a minute, we will check if your answer is correct or not. So your time starts now. Okay, now let's check. Number 1, there are two significant figures. Number 2, 4. Number 3, 3 significant figures. Number 4, 4 significant figures. Number 5, only 4 significant figures. Number 6, 4 significant figures. Number 7, 2. Number 8, 5. Number 9, 7, because this is only scientific notation of 5,300,000. And then for the 10 example, there are 6 significant figures. So I hope you are all got perfect scores. So now let's move on to the next lesson, rounding up significant figures. So there are several rules in rounding up significant figures. The rule number 1, if the digit to the immediate right of the last significant digits is less than 5, do not round up the last significant digit. For example, let's say you have the number 43.82 and you want to round up to the nearest tens. So the answer is 43.8 because you cannot round up this number because 2 is less than 5. So next, rule number 2, if the digit to the immediate right of the last significant digit is greater than 5, you round up the last significant figure. Example, let's say you have the number 234.87 and you want to round up again to the nearest tens. So 234.87 will become 234.9 because 7 is greater than 5. For the last rule, if the number to the immediate right of the last significant is a 5 and that 5 is followed by a non-zero digit, round up. For example, 78.67, then you want 3 significant digit only. So this will become 78.7. Okay, now let's proceed to scientific notation. In studying chemistry, this involves numbers with a large value or a small value. Writing the powers of 10 exponents, called scientific notation, are used to specify large amounts, such as the distance between stars and planets. Earth to Moon distance is about 4 by 10 raised to 5 kilometer. It is more easier than writing 400,000 kilometer. Those with negative power of 10 exponents, negative power of 10 exponents, called scientific notation, are used to specify very small decimal amounts, such as the distance between the silicon atoms in a silicon crystal, which is 2.35 times 10 raised to negative 10 meter. Scientific notation allow us either in very large and in very small number using power of 10. So there are several rules in scientific notation. Rule number 1, standard scientific notation is the number from 1 to 9 followed by a decimal and the remaining significant figures and an exponent of 10 to hold the value. For example, 6.478 times 10 raised to 2 is equal to 6.478 times 100 or same as 647.8. Then 8.65 times 10 raised to negative 3 is same as in 8.65 times 0.001 or equal to 0.00865. So rule number 2, when the decimal is moved to the left, the exponent gets larger, but the value of the number stays the same. Each place the decimal moves changes the exponents by 1. If you move the decimal to the right, it makes the exponent smaller by 1 for each place it is moved. For example, 6897 point times 10 raised to 0 is equal to 689.7 times 10 raised to 1 or 68.97 times 10 raised to 2 or 6.897 times 10 raised to 3. Rule number 3, to add, subtract in scientific notation, the exponent must first be the same. So, for example, we have 3.0 times 10 raised to 2 and 6.4 times 10 raised to 3. So these values have different exponent. So since 6.4 times 10 raised to 3 is equal to 64 times 10 raised to 2, we will use 64 times 10 raised to 2 instead for us to have different values but same exponent. Now we can add these two. Okay, then we must change the 6.4 times 10 raised to 3 to 64 times 10 raised to 2 to add these two values. It changed into 2 and move this decimal point to the left. Okay, now we have 64 times 10 raised to 2. Then let's add. So 3 plus 64 is equal to 67 times 10 raised to 2. So the number 67 times 10 raised to 2 is mathematically correct, but the number in standard scientific notation can only have one number to the left of the decimal place. Therefore, the answer is 67 times 10 raised to 3. So 6.7 times 10 raised to 3. Okay, so we have decimal point here. So this decimal point will move to the right or between the 6 and 7. By moving this one, or this move will add in the exponent. So instead of 2, we will make it 3. Okay, so 67 times 10 raised to 2 is now 6.7 times 10 raised to 3. So this is the answer. Rule number 4, to multiply, find the product of the number, then add the exponent. For example, we have 2.4 times 10, 2.4 times 10 raised to 2, multiply by 5.5 times 10 raised to negative 4. So we will multiply first the whole numbers such as 2.4 multiply by 5.5. So 2.4 times 5.5 is equal to 13.2. And now we will add the exponent, the 2 and negative 4. So 2 plus negative 4 is equal to negative 2. So we now have 13.2 times 10 raised to negative 2. So same with the example in the last slide, that standard scientific notation can only have one number to the left of the decimal place. Therefore, the answer 13.2 times 10 raised to negative 2 will change into 13.2 times 10, or 1.32 times 10 raised to negative 1. 1.32 times 10 raised to negative 1. So how did this happen? So in 13.2, we will move, so this is 13.2, we will move the decimal place to the left or between 1 and 3. Okay, 1 and 3. So the action we did is equal to 1. So 1 adds to the exponent, making the exponent negative 1. So this is the answer. 1.32 times 10 raised to negative 1. But if you use scientific calculator, your answer will be 0.132 or 1.32 times 10 raised to negative 1. So now let's move on to rule number 5. To divide, find the quotient of the number and subtract the exponents. So for example, we have 3.3 times 10 raised to negative 6 divide 9.1 times 10 raised to negative 8. So the first step is we need to divide 3.3 divide 9.1 is equal to 0.36. Then we need to subtract the exponent. Negative 6 minus negative 8 is equal to 2. So if we combine the two answers, we will have 0.36 times 10 raised to 2. So 1 move to the right is minus 1 to the exponent, and 1 move to the left, add 1 to the exponent. So in this case, we will move the decimal place to the right, so the exponent will become 1, and the whole number or the coefficient will become 3.6. So 0.36. So we will move the decimal place to the right. Okay, so 3.6. Okay, then 2 minus 1. So this is the answer. So in writing your answer, you don't need to write the exponent because any number raised to the power of 1 equals to the number itself. So 3.6 times 10 raised to 1 is same with 3.6 times 10. So this is the answer. So now let's convert exponent to whole number. So this exponent will convert into whole number. Okay, so the rules are, if the exponent is negative, move decimal point to the left. So negative, move the decimal point to the left. And if the exponent is positive, move the decimal point to the right. Okay, then add zeros if there is an empty gaps. So example number 1, the exponent 3, the scientific notation 2.31 times 10 raised to negative 3. So, negative, move decimal point to the left. So, 2.31, we have negative 3. So, fill the empty gaps. So, 1, 2, 3. So, here. So, we have 0.00231. Same with this. Okay, then, next is 1.49600000 times 10 raised to 8. So we need positive, we need to move the decimal point going to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, then next, positive again, move the decimal point going to the right. So 1.5. So 1, 2, 3, 4. So fill the empty gaps with 0, 1, 2, 3. So that is 15,000. And then 5.8 times 10 raised to negative 4, negative, move decimal point to the left, 5.8. Then we have negative 4. So 1, 2, 3, 4. So fill the empty gaps with 0, 1, 2, 3. So this is negative or 0.00058. Then how to convert whole number to exponent? We first write out the first few non-zero digits and place the decimal after the first digit. For example, we have 3,000,000 per 100,000. 3 and 4 are non-zero digits. We place a decimal point between 3 and 4. So here the decimal point. Okay. So now we count, you jump 6 places from the last 0 and before 3. Since it's going to the right, the exponent is positive. Okay, so we need, for example, this is 3,000,000 per 100,000. This is the decimal point. So we need to move going to the right because this is positive. 1, 2, 3, 4, 5, 6. Okay, so we need to write it in scientific notation or exponent. So 3.4 times 10 raised to 6. So this is the answer. Okay, then next, how to convert whole number to exponent? If the number is smaller than 1, meaning the exponent is negative. So for this, we need to move going to the left because this is negative. So 1, 2, 3. Okay, so we have 5.2 times 10 raised to negative 3. So this is the answer. So now, I will test your knowledge about conversion of whole number to scientific notation. Okay, I will give you a minute to answer this. Then after a minute, we will check if you are correct or not. Okay, your time starts now. Okay, let's check. Number 1, 5.27 times 10 raised to negative 4. Number 2, number 3, number 4, and number 5. So I hope that you all got a perfect score. So thank you for attending this class and keep safe always. So these are the references in this video.